So imagine you are standing in the center of just this massive echoing stadium. But it's not a sports crowd, right? Surrounding you are like 10,000 highly specialized experts. You've got financial analysts who, only deal in renewable energy markets. You have Python coders who are just completely obsessed with optimizing
Quantum
microservices.
computing researchers, supply chain logisticians.
Exactly, all of them. And you have a highly specific, incredibly complex problem that you need solved right this second. And out of those 10,000 people, only one possesses the exact right combination of skills to help you.
Just one.
Just one. And here is the impossible constraint for you. You only have a fraction of a second to find them. You can't, broadcast a message to the whole stadium over a PA system, and you obviously can't interview them one by one.
Because that would take years. It fundamentally breaks how we traditionally think about searching for resources, right? If you apply our standard, search paradigms to that stadium scenario, the entire system just grinds to a halt before you even locate your first candidate.
Yeah, exactly. And welcome to today's deep dive. Because we are looking at the foundation of our AI-driven future today. The invisible plumbing that basically has to be laid down for the next generation of technology to actually function.
The stuff happening behind the scenes.
Right. We are pulling apart a state-of-the-art foundational generative AI paper. It's titled GRAIL, a deep granularity hybrid resonance framework for real-time agent discovery via SLM-Enhanced indexing.
Quite a mouthful.
It is, yeah. Authored by Jinliang Zhu. And it directly tackles this exact stadium problem we just talked about, which is arguably, the biggest bottleneck in computer science right now.
It really is. And the broader context here, for you listening, is the shift toward the Internet of Agents.
Right.
For the past few years, the standard user experience has been, chatting with a single isolated bot.
Like a monolith.
Exactly, monolith. Yeah. But we are moving away from that. We're moving toward multi-agent systems where thousands of specialized narrow AI agents actually collaborate behind the scenes to execute these massive complex workflows.
Right, so the single bot is kind of dead or dying, and the swarm is the future. But for a swarm to work, they have to be able to talk to each other, and I guess more importantly, they have to actually find each other.
Right, and we already have the connecting cables for that. Standard protocols are emerging, like Google's A2A protocol or Anthropic's Model Context Protocol.
ADCP.
Yeah, so think of those as like the universal USB-C cable for AI systems to physically plug into one another. But having a cable doesn't solve the routing problem. Agent discovery is the missing link here.
Right, because if I have a USB-C cable, I still need to know which port to plug it into.
Exactly. When a primary AI hits a wall and realizes, oh, I need a specialized subagent, locating that perfect specialist in a registry of thousands and doing it in a matter of milliseconds.
Yeah.
It's a massive infrastructural hurdle.
And the paper makes it brutally clear that our current methods for doing this have just hit a brick wall.
Yeah.
The industry is essentially trapped between two terrible extremes right now. So on one end, we have what the paper categorizes as LLM-centric parsing.
Right. The think then look up method. Which, the logic seems pretty sound on the surface, right?
Sure, it sounds smart.
Yeah, you take a massive trillion parameter large language model, something like Gemini 3 or DeepSeek, and you use its immense cognitive reasoning power to just read the user's intent, structure a highly detailed query, and then scan the database.
Like having a genius read the requests.
Exactly. It leverages that raw intelligence to understand complex nuance.
But the trade-off, though, is time. The empirical analysis in the paper shows that relying on a massive LLM just for this parsing stage consumes, over 30 seconds per query.
Which is an eternity.
Right. If an automated workflow requires an agent to consult 3 other agents to finish a task, you are suddenly waiting 2 minutes just for the routing mechanisms to finish shaking hands.
Yeah, it's prohibitive latency.
Yeah.
In the realm of high-frequency agent-to-agent negotiation, the 30-second delay just shatters the viability of real-time multi-agent systems.
Yeah.
It's completely unworkable.
So because that computational cost was unsustainable, the industry violently swung to the other extreme, right?
Yeah, to monolithic dense retrieval. So this approach bypasses the massive LLMs entirely during the live search phase. It leans on lightweight vector databases instead.
Which is fast.
Incredibly fast. It drops the latency from 30 seconds down to just mere milliseconds.
And here's the massive catch. The vector database forces compression. You take an agent's entire multi-page identity, so every technical spec, every capability description, every single historical usage example, and you squash all of that text down into a single embedding vector.
Right, you're translating a really rich, nuanced profile into a single coordinate point in high-dimensional space.
Which the paper identifies as coarse-grained compression. And that leads to a critical failure called semantic drift.
Right, and semantic drift essentially means the mathematical representation has completely lost the plot of the original text.
Like a bad game of telephone. Sort of, yeah. When you force a massive amount of distinct, highly specific information into one mathematical average, the defining edges of that information are just sanded off entirely.
So, to put semantic drift into a real-world perspective for you listening, compressing a rich profile into a single vector is, it's like taking a master chef's 10-page culinary resume and summarizing it mathematically as simply makes food.
Yes, that is the exact problem.
Well, you completely lose the vital constraint that this specific chef specializes in, say, vegan pastries for destination weddings. So when your system searches for a wedding baker, it just reads the makes food vector and hires a barbecue pitmaster.
And sure, it happens in 10 milliseconds, but you get a completely useless result.
Right, a really fast failure is still a failure.
Exactly. That loss of granularity is the core problem the GRAIL framework sets out to solve. Because an architecture that takes 30 seconds to think, or an architecture that instantly hires a pitmaster to bake a cake, they are both completely unviable for a real-time Internet of Agents. So GRAIL, which by the way stands for Granular Resonance-Based Agent AI Link, it doesn't just try to optimize these broken systems, it completely redesigns the architecture.
From the ground up.
Yeah, it decouples the discovery process into 3 separate dimensions: tags, context, and intent. So instead of one massive text block being squashed into one database, the system tackles the agent's identity layer by layer. Let's look at how they replace that 30-second massive LLM first. They introduce SLM-Enhanced prediction.
Right, so instead of firing up a generalized giant model online every single time a request comes in, GRAIL uses a highly specialized 3 billion parameter small language model, an SLM.
Which is tiny by today's standards.
Very tiny. And this SLM has one single function. It reads the user query and predicts the relevant capability tags. That's it.
And what makes this incredibly fast is that the SLM's output vocabulary is strictly clamped to the system's predefined tag set, right?
Exactly. It isn't generating open-ended text. It isn't writing poetry or chatting. It is rapidly classifying. And because of this bounded output, its inference time drops to under 50 milliseconds.
Oh, wow. So instead of like a slow, thoughtful scholar reading every single resume in the room, the SLM is more like a hyper-caffeinated switchboard operator.
That's a great way to put it.
A query comes in, the operator instantly identifies the 3 relevant tags and just routes the search down those specific physical wires. It creates what the paper calls a sparse index, a hard constraint filter.
Right. It instantly narrows the field. But a switchboard operator relying purely on tags is going to hit a wall eventually, because real humans, and honestly even other AI systems, we don't formulate our queries using perfectly clean taxonomic tags.
No, we use messy, jargon-filled, casual phrasing like, fix my computer.
Exactly. The paper refers to this as the vocabulary mismatch. So a formal software agent might have a capability description that reads, optimizes human capital management workflows via deterministic state machines.
Which is quite the sentence.
Very formal. But a human user is going to type, help me automate employee onboarding. And if your retrieval system relies strictly on exact semantic matches with that formal technical documentation, the search fails entirely.
Because the user and the agent are essentially speaking 2 completely different dialects.
Right.
And this brings us to GRAIL's second dimension context, and an innovation they call pseudo-document expansion. So if they need to fix that vocabulary mismatch, they must be building some kind of translation layer, right?
They are. But the brilliant part is they're doing it offline to preserve that sub-second live search speed.
Oh, interesting. So before the search even happens.
Before the search index is even finalized, they point a generative LLM at the agent's formal technical description, and they instruct the LLM to generate dozens of synthetic, hypothetical user queries.
So it's basically guessing what a human might say.
Exactly. It simulates all the chaotic, informal ways a human might actually ask for this specific tool, and then they stitch those synthetic queries directly into the agent's official description.
Wait. Injecting synthetic queries? That feels mathematically dangerous. I mean, we spend so much engineering effort trying to get AI to stop hallucinating false information, right? And here they are intentionally baking hallucinated user intent directly into the core search index.
I know, it sounds so wrong.
Doesn't that just corrupt the database with noise?
It really sounds counterintuitive, but it is actually a strategic broadening of the agent's semantic footprint.
Okay, how so?
By using an LLM offline to hallucinate a massive variety of expressions, slang, business jargon, colloquialisms, they cast a much wider semantic net. The core technical capabilities haven't changed at all. The framework is simply appended, like a translation dictionary, to the agent.
Ah, see.
So when a user queries with a messy sentence later, the dense retrieval system catches the general context because the synthetic queries act as a semantic bridge.
And because all that heavy generative lifting is done on the back end during the initial indexing phase, the live search pays absolutely zero latency tax for it. That's actually genius.
Zero tax. It's totally free during runtime.
Okay, so the switchboard operator gives us tags in milliseconds, and the expanded pseudo-documents catch the weird phrasing. That results in a highly accurate shortlisted candidates incredibly fast. But narrowing down a stadium of 10,000 to a shortlist of, say, 50 isn't the finish line.
No, you still need the one.
Exactly. How does GRAIL ensure the agent it finally selects perfectly matches the user's hyperspecific intent?
So this requires diving into the theoretical mathematical breakthrough of the paper. We really need to look at the mechanical flaw of mean pooling.
Mean pooling.
Yeah. Earlier, we discussed monolithic dense retrieval compressing an agent's entire resume into one vector.
Right.
Mathematically, the standard way that compression happens is by taking the embedding vectors of all an agent's distinct capabilities and averaging them together.
So if an agent has 10 different skills, the system essentially adds up those 10 mathematical coordinates and divides by 10 to find the center point.
Exactly. But the paper proves a theorem about why this is absolutely catastrophic for capability search. It causes what they call semantic dilution.
Dilution, like watering down a drink.
Exactly. Think about how vectors work in high-dimensional space. They have direction and magnitude. If an agent is a highly capable Swiss Army knife with distinct specialized skills, say, it excels at Python coding, but also at data visualization, and also database routing, averaging those distinct directional vectors together, pulls the final coordinate into a muddy generic center.
Wait, mathematically, that implies a massive penalty for competence.
It does.
The more skills an agent adds to its profile, the worse it performs in a specialized search.
That is the exact mathematical reality. As an agent's multidisciplinary skills increase, its relevance score for any single specific skill decays linearly.
That is wild.
When a user asks for a Python coder, a highly capable multi-purpose agent literally gets buried in the search results by a vastly inferior agent that only does Python, simply because the specialized agent hasn't had its core vector diluted by other skills.
Oh man, if you've ever searched your company's internal wiki for a specific policy, and the top result is a massive 100-page generic employee handbook instead of the specific 2-paragraph document you actually needed, you have experienced semantic dilution.
That's a perfect example.
If I need a tool to uncork a bottle of wine, I don't care that the mathematical average of a multi-tool's implements equals somewhat sharp metal.
Right.
I just care that it possesses a corkscrew. I don't want the average. I want the specific discrete capability.
Well, GRAIL's third innovation, which they call maxim resonance, abandons the average entirely. This forms their intent index.
Okay, so no more averages.
No. Instead of using mean pooling to compress an agent's usage examples together, GRAIL encodes them as a matrix. It preserves every single usage example as a separate, distinct mathematical entity within that matrix.
Oh, so it refuses to average the tools together. It keeps the corkscrew as a corkscrew.
Exactly. The corkscrew stays a corkscrew. So when a query enters the final ranking stage, the maxim resonance mechanism checks the user's intent against each individual discrete example in the matrix.
One by one.
Yeah, it is scanning for a localized resonance spike. If the user's query resonates highly with even one specific example, if it matches the corkscrew vector, the agent gets a massive relevance score for that query.
And it just ignores all the other stuff.
Totally. The system completely ignores the fact that the agent also has 50 other unrelated skills, preserving the unitary signal strength of the relevant capability.
Wow. So it completely sidesteps the multi-skilled penalty by just refusing to average the data.
Precisely.
But, a framework this complex, you're balancing SLM tag routers, you've got offline pseudo-document generation, and now these discrete matrix resonance comparisons. It feels like it could easily fall apart in application. Computing a matrix of thousands of distinct examples has to take a massive computational toll compared to just checking a single compressed vector.
But it's heavier math.
So to prove this actually works, they must have had to build a serious stress test.
They did. Because standard datasets in the industry just weren't rigorous enough to test this. So the authors engineered a completely new benchmark called AgentTaxo 9K.
9K, so 9,000.
Yeah, the scale is immense. 9,240 unique AI agents, to be exact. And they are distributed across 154 different industries. You have agents for environmental science, quantum computing, regulatory compliance, logistics, all operating in the same massive registry.
And to make that a valid test, they couldn't just randomly generate those 9,000 agents, right? There has to be a strict architecture to prevent them all from bleeding into each other.
Right, otherwise it's just a mess. So they utilized the MECE principle, mutually exclusive and collectively exhaustive.
MECE, okay.
Yeah. When generating the subdomains for the 154 industries, this principle ensured there was absolutely no semantic overlap. Every single agent was assigned a distinct, non-overlapping functional niche.
So no two agents do the exact same thing.
Exactly. And by creating these incredibly rigid, clear boundaries between agents, they constructed a much more hostile environment for a search engine. It forces the retrieval system to be hyper-precise because close enough is mathematically incorrect in this dataset.
Okay, so they drop 9,000 strictly defined agents into the database, and then they throw over 27,000 distinct queries at them. Capability queries, scenario-based pain points, short keywords, basically simulating the absolute chaos of real-world user behavior.
All the messy ways people actually ask for things.
Right. So in this obstacle course with the latency overhead of the matrix comparisons, does it actually stay under the sub-second threshold?
It does. And the results elevate GRAIL from just like a clever theoretical paper to a definitive foundational framework. On this massive dataset, GRAIL's end-to-end latency averaged 394.48 milliseconds.
Under half a second.
Under half a second. Compared to the massive LLM-centric baseline we talked about earlier, to put over 30 seconds to parse queries, GRAIL delivered a 79 times reduction in latency.
Wow.
The architectural decoupling actually worked.
So it definitively wins the speed race against the massive models by a landslide. But what about accuracy? Did it beat the monolithic dense retrieval approach that relied on those diluted average vectors?
Oh, it demolished it. To measure this, we look at a metric called recall at 1. Meaning, if you only look at the absolute top #1 recommendation the system hands you, how often is it the exact right agent?
Ah, okay. The bullseye.
Right. The traditional dense retrieval method sat at a recall at 1 of 43.94%. GRAIL leaped to a recall at 1 of 71.54%.
But it's a massive jump.
It is. And if you look at its top 10 recommendations, it provided the correct agent over 91% of the time.
That's practically a generational leap in search accuracy. But wait, looking at the baseline data from the paper, there is a massive glaring anomaly here.
You notice the LLM baseline.
Yes. I understand that the LLM-centric routing getline was 79 times slower. But since it was using a state-of-the-art model, a massive engine with billions of parameters dedicated entirely to deep reasoning, shouldn't it have at least achieved the highest accuracy?
You would think so.
Right. Even if it took 30 seconds to think about it, shouldn't raw intelligence win out in the end?
This is arguably the most disruptive finding in the entire paper regarding current AI development trends. The massive LLM router only achieved a 36.84% recall at 1.
Wait, 36%?
36%.
That means the most computationally expensive, supposedly intelligent model performed tangibly worse than the basic compressed vector search.
Yes, the massive model was demonstrably less capable at this specific task.
But how? How does a trillion-parameter model lose to a basic mathematical vector search?
It comes down to the structural limitations of how large language models process vast amounts of information, specifically regarding their attention mechanism.
Okay, unpack that.
When you feed a massive registry of thousands of agent profiles into an LLM's context window and ask it to reason through them to pick the best one, the model suffers from severe context window noise. It falls victim to a really well-documented flaw known as the lost-in-the-middle effect.
Oh, right, the lost-in-the-middle effect. This is where the model perfectly recalls the information at the very beginning of a prompt and the information at the very end, but completely glosses over the data buried in the middle of a massive text block.
Exactly. Because transformers use self-attention to weigh every single word against every other word, dumping 100 dense agent resumes into a single prompt spreads that attention mechanism way too thin.
It just overloads it.
Yeah, the LLM's reasoning gets overwhelmed by the sheer noise of the candidate volume. It loses the thread. And this empirical finding is a major warning sign for the current industry trend of simply, building larger models with larger context windows to solve every problem.
Right, because bigger isn't just slower. In the context of high-speed search and retrieval among thousands of options, relying on a massive context window makes the system definitively less accurate.
It literally dumbs the system down.
So, synthesizing all of this, what GRAIL proves is that the future of the Internet of Agents isn't going to be built on a single, monolithic, omnipotent AI trying to juggle everything in its head at
I
once.
don't know that at all.
GRAIL marries the deep, nuanced understanding of language models with the lightning speed of mathematical vector search by breaking the problem down. It uses a small language model to route tags in 50 milliseconds.
Heck?
It uses offline LLM generation to catch weird human phrasing without paying a latency tax.
Check it.
And it uses maxim resonance matrices to find the exact specific capability you need, completely bypassing the semantic dilution of averaging a profile together.
It proves that the underlying infrastructure for massive multi-agent systems is actually viable today.
Yeah.
The invisible plumbing works.
It is a brilliant technical blueprint. But, I want to leave you listening to this with a slightly more philosophical takeaway based on the mechanics of this paper. Yeah, because the data here vividly illustrates that giving an intelligence too much context at once, like the massive LLM drowning in that lost-in-the-middle effect, or mashing all of a subject's diverse skills together into a mathematical average like the mean pooling approach, actively degrades performance. Averaging out distinct traits just creates noise and semantic mud.
It's true. A system searching for excellence cannot parse a diluted average.
Right. So if the absolute best, most mathematically rigorous way for hyperintelligent systems to communicate their value is by breaking their identities down into ultra-fast, granular tags and highly isolated specific examples, well, what does that say about how we communicate our value in human workflows?
That's a fascinating way to look at it.
Next time you are trying to prove your worth, whether you are, fighting to be heard in a chaotic corporate meeting, pitching a client, or updating your resume, remember the core lesson of GRAIL. Don't hand people a dilute, muddy average of everything you do.
Don't give them the makes food vector.
Exactly. Don't force them to parse a massive wall of text hoping they find your best qualities. Give them the precise tags. Give them the maximum resonance of your absolute best, most specific example. Because whether you are navigating a stadium of 10,000 AI agents or a stadium of your peers, the only way to be found in the noise is to be granular, specific, and resonant.